Hi, my name is Amrendra. He is Kulbhushan. We are from VIU. It's a PCCW media company. And this is who we are. So the domain which we are from is recommendation and personalization. He generally writes the algorithm and the modeling part. I am mostly responsible to take the model live with APIs and clustering, Kubernetes, and all those jazz. So the problem with recommendation when we started in 2016-17 was first the scale. So you have 13 plus million users. You have some 17 countries that we are live in. You have the content. The number of contents is huge. It's like 300K plus movies and TV shows. And the area that we get for the mobile app is only this much, which has like 3 by 3 probably. I don't think much of the people do a scroll and then do a horizontal or vertical scroll all the way to the rightmost part. That doesn't happen. That we have figured out from the inside. So the area that we get is very small, and that is where precision comes into the picture. So since the contents are more, we are mostly very specific on what to recommend and how to drive the journey of a user on our platform. So being consumption and consumption is one of the scale problem as well, because we have n number of new users. Like every day you get 17K new users on our platform. We don't have recommendation history. We don't have their viewing history. So we have to generically recommend them based on what is being running in that particular location. So there is this location services comes into the picture. Regional limitations are there because people from Malaysia would not like to see Indian movies. So that is one regional constraint that we have. Regional constraint also refers to when we talk about one of the rights of one country not being applicable in a different country. So even if we generate like hundreds of recommendations for one user, we have to again filter it out to find the top 5 or top 10 recommendations that can best suit his taste. Now, when we talk about, when we do all these, we actually process all these and keep it in a data store. And by the way, we are on to Google Cloud. How many of you guys have seen GCP? AWS? A lot more. And data centers? Okay. Okay. So we were onto data centers before, but because of scale, we moved to AWS first. And then right now we are in 2.0 model of cloud where we are on partly on AWS, partly on GCP. So there is cross-cloud call, there is inter-VPC calls. So all these adds up to latency. So recommendation gets generated into GCP, but since rest of the legacy systems are on AWS, the cross-cloud calls happen. That itself takes like 100 millisecond minimum. So that is one factor. The types of recommendation that we have is, first one is top trending. This is something that we experimented that can recommendation really help us? Because we didn't know. Investing in machine learning is a little bit costlier from the company's point of view, and the models may run, may not run. So let's test whether a recommendation in its initial phase, like trending. So what is trending in your region? So let's say if we see what is trending in Malaysia, if we bring that row up, like the one that you see over here, top trending. Now that performed well. And when I say that performed well, the CTRs, the click-through rate that we get was nearly 33% than the normal row performing in this particular section. Now when we talk about AB here, we need to figure out that let this be the second row that we have on the home page. Now second row, programmed is something equivalent to where a person sits, figures out what could run better in this country. He will put his own rows, like best of Salman Khan in India, let's say the movies are out. So he programs something versus the system generating top trending. And that's where the AB test runs. And top trending brought about 34% more click-through rate. So now we know that the recommendation works. Now, trending generally comes from a SQL-based query where any data scientist can run that. It's very simple. You have, we use BigQuery as our big data set from Google Cloud, and we generally run queries for past 30 days for country, and we bifurcate it by country. So that gives me top trending for particular country. Now, next is because you watched. This is an ML component. Well, I'll let Pachari talk about it.
Hello, yeah. So before I talk about because you watch, I want to go a little bit back. And Amar has already explained most of the challenges what we face on the recommendation. But apart from that, what it mean by recommendation in VIU? Basically, so what it mean by recommendation is we want to shorten the discovery time of the user so that he spend most of the time in watching the content rather than spending time on the discovery. And it gets mapped to the basically our key engagement metrics like content open rate and the video minutes per unique users. Now, for the CTR for top trending, which I'm going to talk about, and each region has different CTRs basically, and we do AB. For the top trending on Indonesia, we saw more than basically 4 times jump in the click-through rates, but we don't see too much improvement in the video minutes. So even though users are clicking on the trending content, but their video minutes are not improving further. So now here is the one where we try to improve the discoverability of our content catalogs, because what Amar mentioned, there are around 300 Ks content. Now how we make sure ki user get the relevant content and so that he can watch it faster. So to solve that problem, can you go to next slide? Yeah. So to solve that problem, what we came up with the traditional because you watch. This is based on basically this is based on the content-based metadata. What it does is it takes the metadata of each content like cast, actor, genres, and then what we do is we apply the term frequency and inverse document frequency to calculate the similarity. But the problem with term frequency and inverse document frequency is it does not capture the semantic relationship between the words. For example, let's say we have a genre of love and romance. But term frequency cannot match that because term frequency is not semantically related between the words love and romance. So to solve that, what we use is we use the word-to-vec model as well. And then we use the soft cosine similarity to do the weighting according to the TF idea, because term frequency is captured the which of the word is important to the what catalog. And using that soft cosine similarity, we are able to match it more semantically. For example, as you can see here in the Queen Sandok, so because somebody has watched Queen Sandok, which is a little bit on the historical side, and the first recommendation what we got there is basically is the emperor, which is more of a historical. So those kind of semantic relation is being captured by this because you watch model which we have deployed. And on the performance wise, here we get again 3 times jumps in the video minutes, 3 times jumps in the content open rate, sorry, and approximately 25% jump in the user consumption. Basically, each user, so like 3 times more user are watching from this row, and they are watching 25% higher, basically. But still, it is not personalized because we are not using the user consumption data. So till now, what we are using is we are using only the content metadata. There is no involvement of the what users are watching in that region. So even though we have done the global level statistics, which Amar talked about the trending, but what I think is having a more personalized recommendation is something which is needed. And on the home page, typically, we have around 30 to 35 rows, and our recommendation team goal is to come up with as much as rows automated using the different AI algorithm. So basically, we want to power most of the rows using the AI algorithms, basically. Now, coming to the next algorithm, which is topics for you. So this is based on the basically traditional collaborative filtering algorithm. And instead of using a traditional collaborative filtering algorithm, which uses basically a point-wise loss, we uses a pair-wise loss here. And the model which we have deployed is a ensembles of different model. It's not just one model. So here we use meta information as well as the consumption information. And basically it is the pairwise loss is basically what you do in the pairwise loss is you randomly pick a user and the positive item which he has watched, and then you randomly pick a negative item which he has not watched. And what you do is basically when you pass that those user and items to a network, what happens is your distance for the positive item should be lesser than the distance for the uh, uh, negative item. So that's how you learn those embeddings, and basically you power this personalized algorithm. So the power of this algorithm is we get almost 4 times improvement in the CTR, but what we saw is we got around 2 times jump in the video minutes consumption, because this is based on what user are behaving, and that this is the most personalized algorithm. And currently, as a team, we are also working on improving this algorithm further, because one model is deployed, and as a team, we keep on iterating those model. Now, uh, each of these types of recommendations poses different challenges on the caches. So I will let that Amar answer all those questions.
So here there are 3 types of models that we use. One is the user model, where you actually see what has the user done in our platform, how many videos have you watched, how many minutes of video have you watched. The second is the default model. So imagine collaborative filtering gives you a map of X by Y, and what are the top 10 overall content that has been proposed by the whole matrix. That gives me a default model that is, let's say, where we use that is, let's say a user comes and if he doesn't have a viewing history, we actually can give him at least some information on what is running on our platform. Okay, this is a little bit different from trending, because in trending you actually see the location location as a parameter. Here location does not come as a parameter. And the second one, and the third one is the CID specific model. So you have synopsis of every movie. You figure out how much closer the two synopses are. So there he uses the ML technique. So now here what I'm mentioning is an architectural overview. This is a very, very high level overview. Trending on the first one that you see over here, this actually is a pre-processed data. Again, the data is stored in Redis, but it is being pre-processed from warehouse that we use as BigQuery, and we process it and keep it in trending. One of the best things about Redis is even if the data sets are higher, it doesn't affect the response time of it. And the data can be regionally divided as well. This second model that you talk about is the in-house recommendation service that again runs on Kubernetes cluster based on Dockers and has a ML processor at the backend. Here also we can cache at least the default recommendations that is being recommended per country, plus the content-wise recommendation, which is CID specific. But person-specific recommendations, we don't cache it, because one, the person keeps on changing his behavior, and second, the number of users keeps on increasing a lot. So we don't cache that as of now. But the two keys that we have, we cache it here. And the last one is, again, user-specific recommendation. This is where, let's say you have default for Malaysia or default for Indonesia. These two, we cache it. In this architecture, we also have provision for external recommendation systems like AutoML. This is one of the recommendation systems from Google. We have partnered with Google in their alpha phases to build this system. We can hook up any other ML services as well, where it will need the user interaction. It might need the historical data. We can provide it from data warehouse. And then the content management system. Content management system is where we store the geo information, rights management, synopsis, cast, all these metadata of a particular content, which also drives our recommendation. We have seen it in that we call it as meta-based recommendation. So all this power onto AWS, which is the recommendation service. It has a EKS cluster there, and then that is powering our UI. If you talk about the performance, the average latency without Redis was somewhere around 630. With Redis, it came around 94. There are a lot many compute that happens, and that's why you see a 94 millisecond response. But if you see the difference, it is quite huge. This is where Redis helps a lot. How did Redis enter VIU? Initially, back in our days when we were in data centers, we started with single node clusters. This was on DC. Then we moved to AWS. It has ECS, Elastic Cache. Then we started moving on to Google Cloud, which has again memory store. We call it as Google Memory Store. We right now also advantages as we right now also started caching the content as well. So contents are generally delivered to you in pieces. I mean, the rendering happens in pieces. So the edge where the one rendering stops and the other rendering starts, that's what comes from Redis as well. So we have a start and an end of each content byte. That's what drives the content seamlessly. That has also started happening right now on Redis. We see consumers, we have a system called it's user management. There also we see Redis as one of the core caching technology that we use. When we used to have billing as partners, so let's say you have Airtel running on you have Airtel streams. These things had movies or other OTT platform interactions. The billing used to happen through carrier. So you can bill via your wallet, e-wallet, and that's where we started using Redis when there were double billings on particular user. So Redis was used as the centralized cache, and we don't have to call on billing for every time the user logs in to see a particular movie or video. So this is how Redis got into VIU, and that's all I have. Do you have any questions?